Good afternoon, good morning, and good evening to everybody from the various time zones who are joining us in this live stream. I'm Abhirup, and along with my co author Mary, I'll be talking about our ongoing work on designing a functional programming language for programming IoT applications. This project is a part of a larger project called Octopi, which also considers the security aspect of these applications. To set the stage for the problem statement, IoT devices are ubiquitous. Their numbers are increasing every day. As of today, there are 31 billion devices deployed, and in the next 2 years, another 5 billion devices are predicted to be deployed. They are ubiquitous. They are found everywhere. They are found in smart cars, in logistics, in traffic controllers, in medical devices, and a variety of applications. So this diversity in applications of IoT devices leads to the fact that there are a diverse set of architectural choices that are available. To give you a few examples, these are the more popular IoT boards called like the ESP32 and the STM32 boards. As you can see, their memory starts from up to 4 KB of RAM, and they can go up to 1 megabyte of RAM, so they are quite memory constrained. On the other side, there are more powerful boards like the Beagle boards or the very famous Raspberry Pi, which can have up to 8 GB of RAM, and these are used in more powerful edge IoT devices. So a natural question which arises in the mind of a programming language researcher is, how do we program such a wide variety of devices? And as of today, the majority answer to that question is, well, C. So C is C has a very robust tool chain. All of these manufacturers, they provide at least some access to some kind of ARM-based C compilers, and it's actually quite widely used in these devices. So if we look at the TOB language index, it seems to concur with our finding. So the latest findings of the TOB language index shows that C is now the most popular programming language in the world. I believe it was ranked third or fourth a couple of years back, but now it's again ranked one. And I was looking at the reason of what led to this sudden rise in C, and there was a note associated with this ranking. And the main point that it was making is again that in embedded software, C and C++ is being used more and more. So I believe it is quite well established in the programming language community that C doesn't have very well-defined semantics. It has lots of undefined behavior. It's memory unsafe. So it's perhaps not a great idea to continue to program in C. So we are looking to program IoT applications in more high-level languages. So the Octopi project took two different research routes to solving this problem. The first one is called Haskell, which is an embedded DSL, which is embedded inside the Haskell programming language. It was presented in Haskell Symposium just last month. And what today we'll be talking about is a standalone programming language called Hailstorm, which is not embedded in any language. It is a language of its own. So let's start talking about Hailstorm. We show a very simple example of calculating a nth Fibonacci number. We are going to look at some syntactic properties of this program as well as semantic. First of all, this is a functional programming language. This supports higher order functions, recursion, partial applications. It's a pure language. This particular snippet might not impress that fact, but when a function in Hailstorm says Fibonacci int to int, what it means is that it will take an int and it will transform into an int, and it will guarantee that there is no IO or any kind of stateful operation. If that is happening, then it will be reflected in the type of the function. It is statically typed, as can be seen from the annotations in each of this function. The top level function has to be annotated like fib help or fib here, but at the lower level we try to infer the types. And this is a semantic property. Hailstorm is call by value because the cost model of call by value, we found this to be much more predictable than something like call by name. And also it's a domain specific language. It was not designed for general purpose applications. But it is not an embedded DSL. It's a standalone language. So we want to linger on two of the more interesting properties of Hailstorm, which is purity and static typing. Well, while purity gives you some form of way to equationally reason about your code, it also enables a lot of compiler optimizations like inlining, fusion. So from a compiler writer's perspective, it's quite convenient to deal with a pure surface language. Well, for static typing, it obviously gives you a very preliminary static analysis tool, but it also allows you to track certain information in your type system, like say resources or data flow, and the combination of these two properties can actually be used to prove the security of your program. And this result was presented by one of my colleagues at Chalmers, where he showed that when a pure functional language is interfacing with an impure and static or dynamic type language, the pure language is capable of not leaking information and proving that. And we would want to prove such properties for the language. So now the next natural question which arises is, how do we handle effects in our language? Because we claim that this is a pure language, so how do we do input and output? Well, Hailstorm adopts an infinite stream model, or more commonly known as stream-based I/O. In the stream-based I/O, your program is seen as a composition of your functions, which is placed in an input stream which is flowing, and it just simply transforms all the input that is coming in into a new output. There's a notion of a logical time step in Hailstorm, which is that in one time step we try to read from all the sources of input. Say there are 3 sensors, so in one time step we will read one value each from each of these sensors, and in the next cycle we will continue to do that, and it's an infinite process. The input keeps coming and the output keeps going, and there's this logical time step where we read input from all of these things. Now this is quite reminiscent of the old Haskell model, I/O model, where you had a list of responses and list of requests, where Haskell used lazy lists to indicate streams. Now this model was not without any problems. This actually led to really non-modular I/O driven programs, and in case of IoT applications, we will be dealing with a lot of I/O driven programs where I/O is the main component. It is non-modular because of the fact that all of your input and output is forced to happen at the main function, and at the lower level, in the bottom functions, it's not possible to do I/O. So that's not very convenient, and also it's not extensible. Every time you want to add any kind of new I/O operation, you would need to modify all this response and request rates. Unfortunately, a lot of EDSLs also struggle with this very same problem. In our case, we have seen Accelerate, Raw, Feldspar, and in fact, even the Husky IoT EDSL that we talked about earlier, this has a very similar stream-based I/O model. And in case of I/O-driven IoT applications, we cannot have this property. We would like to get away from it. So what we are seeking to do at this point is move away from non-modular I/O code. So we start by taking inspiration from the arrowized formulation of FRP. So in arrowized FRP, you actually program with streams. It's also a form of stream-based programs. It is called Signals in case of arrowized FRP. It provides you a minimal set of composition combinators like serial composition, fan-in, fan-out, parallel composition, and using these very small set of combinators, you can easily make your program more composable. But AFRP, at least the old formulation of AFRP, had the very same problem, that it was also itself an EDSL, and it had to do some kind of stream-based I/O, where at the top level function you would have list of input and list of output, and you would have to map them to each of these arrow combinators. We don't want to avoid that. What we want rather is use the arrowized FRP signals and think if it's possible to represent real-world signals. What I'm trying to say is, for example, take a sensor. Can a sensor be represented using this type, where the void type would represent reading from the real world and int is what you read from that sensor? Does this work? Let's see. Now this program that we see here, this is type correct. So I'm using the fan-in, fan-out combinator and if you see here, there's no type error in this program, but actually this program is semantically unclear. As we said earlier, in Hailstorm, there's a notion of a logical time step, and once time step, you're allowed to read from only each unique devices. So in this case, we are reading from 2 devices, so this program should have ideally been disqualified. Now there's another possible semantic meaning, which is that which we can infer from the type, is that you are reading actually from one sensor, and what that sensor is returning is a pair of integers. But that's not true. That's not what the program is doing. You are actually reading from two sensors. So this leads to very undefined and not very unclear semantics. What we actually want to do is somehow enforce the uniqueness of a resource. And we do that using a concept called resource types. The idea is very simple, which is you tag each resource with some kind of label. What this label does is that it ensures that each of these resources are actually unique. But what now you should also do is modify the FRP combinators as well, so that every time you are composing these resources, for example, we see serial composition here, what it's doing is a disjoint union. This U here implies disjoint union. So if R1 and R2 has any of the common resources, say this has sensor 1, this also has sensor 1, this program will be disqualified because then the resource is not unique. So now using this simple idea from resource types, if we were to write the same function as before, the only change which we have made is now we have annotated this function with singleton union singleton resource type. And what happens in the Hailstorm compiler is that this gives you a type checking error because your resources are not unique, because in one given time cycle you can only read from unique resources. So this gives us a nice way to deal with input and output. The general type of any IO function looks like this. You read from the outside world and you read some kind of value, whether it is int, boolean, float, some kind of monomorphic value. And similarly for output, you write some kind of value, whether it is one of these monomorphic types, and this void again represents is you are writing that value to the outside world. So there are no terms in the language of the type void. This simply indicates that you are writing to the outside world. So now that we have some form of some way to do I/O, it would be nice to write some hello world function. So the hello world in the world of microcontrollers is blinking an LED, and we are just going to show you how to blink an LED. So the board that we will use for blinking an LED are the GRISC boards. So the GRISC board actually is programmed using Erlang instead of C. It uses the Artemis operating system for low-level system calls. The reason why we choose this board is that its tool chain is extremely simple and very intuitive, and it's very fast for prototyping, and it's something whose demonstration we can show you today. What we are going to do is we are going to blink an LED, but we will do a little more than that. We are going to blink two LEDs, and we'll try to blink them synchronously, both of them. We will blink them in two different colors, one with red and the other with yellow, and we are going to introduce some notion of time. We are going to say that let us turn this LED on for 3 seconds, and then it will be off for 3 seconds, then another 3 seconds and 3 seconds, and then the cycle goes on and on. So we need some way to introduce a notion of these 3 seconds, because we have not spoken about the actual wall clock time in Hailstorm. So we do that using the rate combinator. The rate combinator accepts some kind of time step in float, so you can give even 3.5 or 2.5 seconds. It takes a signal function, and what it returns is a modified signal function which has a different sampling rate. And similarly, if you compose various signal functions with different sampling rates, it's going to choose the one with the sampling rate of the rightmost function. We do not have any fancy tactics where we choose the slowest time or anything like that. But for this example, we will just have one single sampling rate. The IO functions that we will use are read LED and write LED. They are annotated with their respective resource. And let us see what this program would look like. So let's just walk through this program. So what this is trying to do is it takes a function called Blinky, and it sets a sampling rate of 3 seconds. So Blinky will run at a sampling rate of 3 seconds. What is Blinky doing? What Blinky does is it reads the status of two LED lights, whatever the color is, and then it just flips the lights. And whenever it's done flipping, it simply writes that out, the flipped colors to the light. And individually, you can see what the read two LEDs is doing. It's just reading these two LEDs, and write LEDs writing them, and flipping is also very simple. We use some form of numeric encoding where we use 1 to indicate red and 4 to indicate yellow. Also, you can see it has now given rise to a modular program where all of the functions are capable of doing some kind of I/O. So let us actually show you by deploying this on actual physical grist board, which I have with me, as you can see here. And the grist board has a SD card. I'm going to take that SD card and I will show you how to deploy my program over there. All right. So let us see what the toolchain for grist looks like. We have already created a Erlang project using Rebar, which is the build tool for Erlang. So this has a src repository where I've already placed the Grisp program, the Blinky program, which I've just shown you in the slide. You can see it's the very same program. I've also placed runtime, a very small layer of runtime. So what this runtime is doing is it is actually doing this numerical encoding, which is doing the serialization and deserialization. You can see right color. When I say 1, it knows red, and when I say 4, it knows yellow. Similarly with red color, read color. So what I'm going to do is I will try and compile, and let me do Grisp, and it has compiled, and you can see that it has created a core file. A core is Erlang's intermediate representation. It is not very readable Erlang, but it is specifically doing the same thing which we have written in the program, but using some very convoluted intermediate representation. So now we're going to show how to deploy that. So I'm going to go at the root of the repository, and what I'll do is I'll call a script which I have already written and is available globally. And while this deploys, let me show you what this script does. So as you can see, what this script is doing, it searches for a drive called Grisp. It clears it up, and then it compiles the entire project. It compiles robot.core, and it just simply places the Beam file that is generated from this core file. So Beam is the Erlang virtual machine, and it has the simple bytecode. It generates some simple bytecode, and we simply place that generated bytecode at the right place. Okay. So now we can see it says that our project robot has been deployed. I'm going to take that out. And now we have unmounted the Grisp board. So what I'm going to do is take the SD card, and allow this program to boot. So the boot takes around 2.5 minutes to complete its booting. So in the meantime, maybe we can proceed with the rest of the slides. So as we can, so I've put a video of what it would look like when this program is deployed, and this is what would happen. They would blink for 3 seconds, it would turn off, and then go for another 3 seconds, and this cycle would go on and on. So apart from the combinators, were very simple arrowized FRP combinators that we have produced here already in the example. There are some more interesting combinators like loop. This is used to emulate state in the language. There's switch, which is a form of multi-way if. And apart from this very contrived example about blinking LED, we have more useful examples. They get progressively harder, and you can find all of them in the rest of the paper. So let us talk a little bit about the compiler itself. So the Hailstorm language has two backends, an LLVM backend and an Erlang backend. We originally wrote the LLVM backend because we wanted to do some optimizations with memory layout and see what is the correct memory layout for each different types of board. The LLVM itself is also capable of generating C. However, we do not have any interesting results from the LLVM backend. The Erlang backend was written solely for the purpose of the Grisp board. Both of them used very standard garbage collectors. We have not added any new research in the garbage collector direction. The Hailstorm compiler is moderately optimizing compiler. It does lambda lifting, inlining. It doesn't inline recursive functions, but as we can see in another one of the small examples where we have a closure where we can see the free variable is usually heap allocated. To reduce heap allocation, what it does is it tries to do some form of lambda lifting, and then it will aggressively inline as long as it doesn't encounter any recursive code. So this inlining feature of Hailstorm becomes very simple because of it being a pure language, and this is actually quite beneficial if we compare it with Erlang, the same language that runs on the Grist board. In that, if we take this very contrived example in Erlang, where you have a set of local variables and you are just plainly adding this. So the Erlang compiler, ERLC itself, is also optimizing, and it can inline this code to as well as constant fold it to give you the correct result at compile time itself. However, if we take the very same function and we lift out these local variables and make them global functions and declare them as function, and you can see it's the very same program, the compiler is unable to inline. And why so? Because it's unable to prove that X, Y, Z are free of side effects. The same program in Hailstorm would inline absolutely fine, because here the type system tells us that, okay, we are dealing with a pure function, so it's safe to inline. So let us talk about the semantics of the language. Here we are seeing a very general program which does input and some kind of output. So whenever we run a program, what happens is that the output wants to write some kind of output. So it will request some kind of data flow from the composition of pure functions here. The function itself will call for some input from the input layer, and then the input will actually start the IO, and then the whole cycle of input begins, and then it's an infinite cycle which goes on. We should make this clear that the pull-based semantics is a property of Hailstorm, the surface language. Underneath the surface, the drivers might have a very push-based nature, and it's actually very common for drivers to be woken up using interrupts whenever there is some kind of push. So how do we deal with that? Well, this is just a simple example driver where I've seen. So we can see that we have a UART driver here where messages are being pushed. So what we do is when new messages being pushed, we buffer them, and when the upper surface language calls for the pull, it tries to look and see that, okay, do I have the data of the given size? If it does, then all right, it gives the data and continues processing. If it doesn't, then it just stalls and the cycle keeps going on and on. So that's how we deal with push-based drivers underneath the language. So we show some micro benchmarks. We do not have very useful baseline, but what this one benchmark is capable of showing is that these functions are extremely IO driven, and as you can see, the computation runs in order of microsecond, and it's quite fast, whereas the IO takes more time, and most of the time is spent done doing IO. In the very same programs, we can see the memory usage, and there is no funny memory allocations happening throughout the program run. The spikes that you see at the end is just killing the application, which perhaps triggers the garbage collector to collect the symbol tables. There's a lot of scope of interesting future work in Hailstorm. First of all, the signal functions types that we have, they can be annotated with another extra piece of information like labels. And these labels, such as security labels, can be used to track information flow. And this is a well-studied area almost 10 years back. So we plan to integrate some of this work into Hailstorm. We would like to have a more robust foreign function interface because a lot of these drivers are written in C. So having a good FFI support is very important in an embedded language so that you can interface smoothly with C. A very different line of work that we are working on is SenseVM. So this is more of a separate backend for the language. What we are creating is a bytecode interpreter for any eager and static type functional language like ML, Elm, or any such languages. Our main goal here is to ensure some kind of portability among the various devices. So the example which we have shown is using Grist board, but in even more memory constrained boards like STM32, ESP32, we would have to change the code a lot, and it's not very portable. The same program in an STM32 is not assured to run the same. We would like to avoid doing that and make that portable. At the same time, ensure some kind of security within the virtual machine. So this is another ongoing work which is going on right now as an alternate backend for Hailstorm. Well, there are tons of related work on Hailstorm. The reactive ML is somewhat representative of the whole synchronous language domain, including language like Lustra, Estrel, which have been successfully used in embedded applications. There's of course Erlang itself, which is dynamically typed, but Erlang has a very nice runtime and a virtual machine which gives fault tolerance capabilities, something which we lack. And the virtual machine work which we are doing right now, we want to be inspired from Erlang's fault tolerance capabilities and integrate some form of fault tolerance into our language so we can describe entire networks of IoT devices. There are also more experimental VMs like Velox, which runs Scheme at the top, and it has some interesting security related results which it has presented, which we are also looking at. There's of course FRP as a programming language. Our language's whole effect framework is based around advanced FRP, so we will continue to take more inspiration from FRP. And there's a lot more details in the paper, not just about the related work, but we provide the operational semantics of the language as well as all the type rules associated with the language in a lot more detail in the paper. And also, in the meanwhile, the board which I was booting has now successfully booted, and as you can see, the program which we were originally trying to write is now working. That's all I had to say. Thank you, and I'll take any questions right now. Thanks.